session on fluid mechanics. In this session, we will discuss the concept of capillarity. Capillarity, also known as capillary action or capillary rise, is the ability of a liquid to flow in narrow spaces or tubes, such as capillaries, against the force of gravity. This phenomenon occurs due to the combination of adhesive and cohesive forces acting on the liquid molecules. Adhesive forces are the attraction between molecules of different substances. Cohesive forces, on the other hand, are the attraction between molecules of the same substance. In the case of capillarity, adhesive forces between the liquid and the surface of the tube or container pull the liquid upward, while cohesive forces between the liquid molecules help maintain the column of liquid. The height to which a liquid will rise or fall in a capillary tube depends on several factors, including the surface tension of the liquid, the diameter of the tube, and the contact angle between the liquid and the tube surface. Generally, liquids with higher surface tension and smaller contact angles will exhibit greater capillary rise. For example, water in a tube will exhibit capillary rise because when you see this is a capillary tube which is inserted into a container filled with water, what happens is water rises here, it forms a meniscus like this, and this is the surface tension which is acting on the surface. This is the contact angle theta. This value is approximately equal to 0 for water and tube contact surface. In water, the adhesive force is more. It sticks more to the surface of the capillary tube. In that case, if you happen to have mercury into this tube, then what happens is, suppose this is the tube, this is the container containing mercury here, there will be a small dip over here that you can see, or depression as you call. This is the value of sigma and this is the angle theta that you see. It is quite large. This theta is approximately 128 to 130 degree. And in mercury, what is more is the cohesive force, that is attraction between the molecules of mercury. So they tend to cling to each other as compared to water, which has more adhesive force, and that is why it will stick more to the surface of the capillary tube. Whereas in case of mercury, it will stick to each other, and that is why you see this dip. And this is the rise edge, and this is the fall edge that you see. Capillarity has various practical applications such as the movement of water in the plants through xylem vessels, the function of paper towels in absorbing liquids, and the operation of capillary tubes in laboratory instruments like microfluidic devices. So these are all the applications of capillarity which you can see around. It also plays a role in phenomena like soil moisture retention and the rise of liquid in small cracks and pores in porous materials. This is also something that you must have seen, that if a particular surface has cracks, then the fluid, because of capillarity, flows through that crack and it moves forward. So these are some practical applications of capillarity which you see in day-to-day life or you can see in nature. Next, we'll talk about the expression for capillary rise and for fall. We'll start with the expression for capillary rise. So here you can see a container which is containing some liquid. We are talking essentially about water. Consider a glass tube of small diameter D opened at both ends and is inserted in a liquid. So as you can see, this is the capillary tube or the glass tube that we have inserted. The diameter of this tube is going to be D. The liquid will rise in the tube above the level of liquid. Now this is rising because the liquid that we have taken is water. As I told you, it is going to rise. Let h be the height of the liquid in the tube. So this is the height h. You can see this is a concave meniscus which has been formed. This is called as concave meniscus. Under a state of equilibrium, the weight of liquid of height h is balanced by the force at the surface of the liquid in the tube. So the equilibrium basically happens because this weight of liquid over here is balanced by this force. Now, when you talk about force, you have to first talk about the surface tension. But the force at the surface of liquid in the tube is due to surface tension that you can see here, sigma, surface tension of liquid. Theta is the angle of contact, as you can see. For water, it will be approximately equal to 0. Now, we will talk about the equilibrium forces. First, we'll talk about the weight of liquid of height h in the tube. This will be area of tube into h into rho into g. We are talking about weight. So this becomes rho gv. If you are aware of this formula, the weight can also be written as rho gv. So it is rho g and v is the volume. So when I talk about area of tube, the cross section area is 5 by 4 d square into rho into g. So this is one of the forces that we are trying to equate, and the other force is the vertical component of surface tension force that you have. Now, when you have to calculate force, this has to be surface tension into circumference. This becomes the force. Now, when I talk about this force, please be careful. This is just showing the surface tension. When I convert this into force, it has to be multiplied to the circumference. And circumference is a circular one. So, circumference is always pi d. So, this will become the force. Now, when I resolve this force in the two directions, along the angle theta, it will be sigma pi d cos theta, and in the perpendicular direction, according to mechanics, it will be sigma pi d sin theta. Now, weight is always balanced in the y direction. So, I'll write over here, this will be sigma into pi d, and don't forget to add the cos theta term. So, this is the term to be added. So, this becomes my equation 2. Now, for equilibrium, we need to equate both of them. So, I'll write here equating 1 and 2 for equilibrium. So, you will have pi by 4 d square into rho g is equal to sigma into pi d cos of theta. What gets cancelled on both sides is the term pi, and one of the d gets cancelled. So what remains over here, okay, I forgot to add the term h, so just add here h. So what remains is, therefore, h is equal to 4 can be multiplied here, so it becomes 4 sigma cos theta, and here what remains is rho g d. So this becomes the formula for H, for capillary rise. Now when I say that it is water, this cos of theta will become equal to 1. So when this becomes 1, H will become 4 sigma upon rho GD for water, because cos of theta is nothing but cos 0 is equal to 1. Now let's talk about the expression for capillary fall. If the glass tube is dipped in mercury, the level of mercury in the tube will be lower than the general level of the outside liquid, as shown in the figure alongside. You can see here, this is the amount of mercury in the container, and in the capillary tube there is a dip. This is the surface tension, as I told you. This is the angle of contact. This h is the height of depression in the tube. Now again, here for equilibrium we need to have two forces. So the first force will be the downward force which is going to act. So we are going to first talk about the surface tension which is acting downwards. So this will be nothing but sigma into circumference into cos of theta. So this will be my first formula, and I have to equate this with another force. So the other force which acts is nothing but the hydrostatic force. You can see here this pressure is actually what is maintaining this level of mercury in the capillary tube, and this is going to be a convex form. So what you will be doing here is the hydrostatic force which needs to be taken into account. So the hydrostatic force will be nothing but P into pi by 4 d square. P in itself is rho gh. So this becomes rho gh pi by 4 d square as the formula. You can mark this as equation 2. For equilibrium, you need to equate 1 and 2 for equilibrium. So I write here the formula as sigma pi d cos of theta is equal to rho g h into pi by 4 d square. So what gets cancelled is pi d, pi d. I want to find the formula for fall. So h is equal to 4 sigma cos theta upon rho g d. That's what remains here. So this is again the same formula that we have derived for fall. So whether it is rise or fall, the formula remains same. But what we need to note is the angle theta for Mercury ranges from 128 to approximately 130 degree. So when I give this, the value of h actually becomes negative 4 sigma upon rho gd and some value over here. Now this negative sign is going to indicate fall or depression. This is what you need to note. So that's all about the principle of capillarity that happens around us and the expression for capillary rise and fall which we need to use further. So with this, I end the session. I hope you have understood the derivations of the concept. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.